Hi everyone. In the last class, we have discussed about the existence of the positive square root of a positive operator. Today we are going to give an application of it. Namely, we are going to discuss about the polar decomposition of an operator. Okay. Suppose if you have a complex number which is non-zero, let us take that is a complex number which is non-zero. Then we can write z as mod z equal I theta for some theta in R. So this is known as the polar decomposition of Z or the polar form of. Okay. Now we can ask the question, can we write down the polar form of a bounded linear operator defined on a Hilbert space? So in this class we are going to discuss about such a result. So before discussing that, let us look at some important information. Let us start with a bounded operator from H1 into H2. Then we know that T star T is a map from H1 into H2, H1 into H1, and it is positive. So once we have a positive operator, it has a positive square root. So let us define modulus of T as square root of T star T. We know that square root of T star T is unique. Hence, this is a linear map from H1 into H1. So this is similar to the modulus of a complex number. We know that modulus of Z is nothing but here modulus of Z is Z bar Z square root of that. Okay. Now this is known as the modulus of T. Okay, that means we are able to replace modulus of a complex number with modulus of the operator here. That means we are generalizing from complex numbers to operators. Now, in general, what can we replace is e power I theta as an operator. Can we generalize e power I theta to an operator? So if you look at e power I theta, so e power I theta, if we take this as an operator, we can take some complex number also. This is e power I theta into e power 1. So that means if you want to generalize e power I theta to an operator, we have to replace it with a unitary operator. That means the question we can immediately try to generalize this polar decomposition of complex number to operator in the following way. So this is the T equal to U mod T, where U is from H1 into H2 unitary. Here unitary means it is isometry plus onto. This is what we expect. But here there is a slight difficulty. If you look at a non-zero complex number, that is invertible, whereas if you take a non-zero operator, that need not be invertible. So here invertibility makes a big difference. When T is invertible, we can conclude that this is exactly the polar decomposition of T. This which is generalization of polar decomposition of complex number. But when T is not invertible, this unitary can be replaced by a partial isometry. So that result we call as the polar decomposition of T. So let us state the result. Let T be a bounded operator from H1 to H2. Then there exists a partial isometry V from H1 to H2 with initial space, null space of T per, and the final space range of T closure such that T can be written as V mod T. In fact, we can say that this decomposition is unique. So this decomposition is unique. That means if T equals to WP, where W is a partial isometry, and P is a positive operator, with null space of T and null space of V are same, then we can say that W is nothing but V and P is nothing but mod. So in this way we get a unique decomposition. So this unique decomposition we call as the polar decomposition of T. Is called the polar decomposition of T. So we can write T as V mod T, where V is a partial isometry with these properties, with initial space, null space of T per, and final space as closure of range of T. And we can say that if there is another decomposition like this with kernels of W and P are same, then we can say that W is nothing but V and P is nothing but mod T. That means if we have a decomposition like T equal to V mod T with kernel V equal to kernel mod T, then we can conclude that it's a polar decomposition. Okay, so let us quickly recall some important properties of partial isometries, and we have just defined what is the modulus of an operator. So let us look at some observations. So let us take for x in H, we have mod Tx inner product with mod Tx. This is nothing but mod T square inner product x with x. Because mod T is a positive operator, we can bring it to the left hand side. It is again mod T. But mod T square is, it is square, see mod T square root of T star T. So mod T square is, this is T star T, x inner product with x. This is norm of Tx square. Okay. So that means we can say that square is nothing but norm Tx square. So this is nothing but so immediately we can observe that null space of mod T and null space of T are same. If Tx is 0, then norm Tx is 0. That implies norm of mod Tx is 0. That means mod Tx 0. This is if and only. So we can conclude that null space of T and null space of mod T are same. The second observation is, if you look at range of mod T closure, this is nothing but null space of mod T per, because mod T is a positive operator. This is null space of T per, because null space of mod T and null space of T are same by the earlier observation, but this is not exactly range of T star per, range of T star closure. Okay, so this is about modulus of the operator. Let V be a bounded operator, then the following are equivalent. V is a partial isometry. V star is a partial isometry. This we have already shown. V star V is projection onto range of V star. V star is projection onto range of V. V star V is V. V star V star is V star. So this can be proved in an easy way using the properties of partial isometries. You can take this as an exercise. Okay, so with these two informations about modulus of the operator and partial isometries, we can actually prove the polar decomposition theorem. So first we have to get a partial isometry V from H1 into H2, so that T equal to V mod T. You want to define a partial isometry, define V naught, an operator from range of mod T into range of T by elements of range of mod T are of the form mod Tx. So mod Tx, where x is coming from H1, is mapped to Tx for all x in H1. We can easily show that V naught is linear. And it's also bounded. V naught of mod Tx, if you look at norm of this, is exactly norm Tx. But we know that norm Tx and norm of mod Tx are same by the earlier observation. So this we can say that V naught is an isometry. It's also onto, because if you take y is in range of T, so y can be written as T of x for some x in H1. Now the corresponding pre-image is mod T of x. So we can also show that this is on. Okay, now we got a map V naught from range of mod t into range of t, which is linear, isometric, and onto. This is a unitary map. We want to extend it to the full space H1. So now we have a boundary linear operator on a space. We can extend it to its closure in a unique way. So let V naught tilde is a map from range of t into range, closure of range of mod t into B, the unique isometric extension of V naught. And in fact, domain we can always extend because V naught is a boundary linear map, and since V naught is unitary, so V naught inverse is also boundary linear map, which is isometric. So V naught inverse also we can extend. That means the codomain also we can extend till the closure of the operator. So unique isometric onto. So it's a unitary extension. Okay, but we want a map from H1 into H2. So define V from H1 into H2 by V of x as V naught tilde x whenever x is coming from range of mod tilde closure, and 0 when x is coming from its orthogonal complement. So that is null space of mod t. So then x is coming from. In other words, how to write this one? Let us take for x in H1, we can write x can be written as u plus v, where u is coming from null space of mod t and v is coming from range of mod t closure, because they are orthogonal spaces, null space of mod t and range of mod t closure. Then define, so v of x is v of u plus v, we are writing as v naught tilde of v. Now we can easily show that now v naught tilde is a unitary map from range of mod t closure into range of t closure. So we can easily check that V is a partial isometry. With null space of V is exactly null space of mod t, and that is exactly null space of t, and range of V is nothing but, so V of H1, but V of H1 is mapped to range of t closure. So final space is range of t closure, and null space of V perp, that is the initial space. So initial space of V is null space of t perp, and final space range of mod closure. We know that for any partial isometry, range is closed. Okay, so we got a map V from H1 into H2, and if you look at V of mod t, so we have V of mod tx. So mod tx is an element of range of mod t, so that is nothing but V naught tilde of mod tx, but V naught tilde is nothing but V naught mod tx on range of t, range of mod t. So that is Tx. So we can conclude that V mod Tx is Px. So we got a partial isometry which satisfies T equal to V mod T. Now we want to show that this decomposition is unique. That means, let us say there is one more decomposition. So uniqueness, let T equal to WP be in another decomposition. As stated, that means kernel of P, null space of P, and null space of W are same. So then we have, if you look at T star T, this is P W star WP. This is nothing but P projection onto range of W star P. This is projection onto null space of W per P, because range of W star is null space of W per, and P is a positive operator. So if I take T star Tx, T star Tx is P multiplied by projection onto null space of W Px. Now Px is in range of P, but range of P is nothing but null space of P per, because P is positive, and null space of P per and null space of W per are same. So this is a projection as behaves like identity. This is P square x. So that means we can say that T star T is P square. But we know that the square root is unique. If you take the square root both sides by taking square roots, we get that left hand side we get mod T, and for a positive operator square root of it is itself, we get P. So we are able to show that mod T is P. That means, so we have T equal to V mod T, and that equal to W WP, that is nothing but W mod T, or we can say that V minus W mod T is 0. So this means V minus W mod Tx is 0 for every x in H1. That means V equal to W on this kind of elements, mod Tx. Mod Tx is nothing, this element of range of mod T, and V minus W is a bounded operator, so we can show that V equal to W on range of mod T. So we can say that V equal to W on range of mod T closure as V minus W is bounded. Okay. Now if you are able to show that V equal to W on the range of mod T closure, so on range of mod T closure per, this is range of mod T per, that is nothing but null space of mod T, that is null space of T. We have Vx is 0, V minus W, x is Vx minus Wx. When x is coming from null space of T, we know that null space of V and null space of T are same, so the first is 0, and we know that null space of W and null space of P are same, but null space P is nothing but again mod T we have shown, so this is 0, so this we can say that. So therefore V equal to W on H1. So we have shown that when we have another decomposition satisfying this property, kernel condition or null space condition, we can show that the partial isometry and the positive operators are unique. So this is the polar decomposition result. Now let us look at some important information. So T equal to V mod T with null space of P is null space of mod T, or we can say that this equal to null space of T. So this is called the polar decomposition of T. Which is unique. So if T is 1 1, then V is also 1 1. Already V is a partial isometry, so it becomes isometry. If T is 1 to 1, V is 1 to 1. Okay. If T star is 1 to 1, then we can say that null space of T star, that is 0, this is range of T per, or we can say that range of T closure is H2. But we know that range of T closure is exactly range of V, so therefore we can say that this implies V is 1 to 1. So whenever T star is 1 to 1, then V is on 2. Both T is 1 to 1 and T star is also 1 to 1. We can say that V is isometry on 2. So therefore, if T and T star are 1 to 1, then we can say that V is unitary. So in general, if this is 1 1 and on 2 is, then we can say that V is unitary. This directly follows from earlier two observations. Okay. So let us look at some more consequences. If T is in B of H is normal, then we know that T star T equal to T star. Then we can easily say that modulus of T, that is T star T power of, this is nothing but T star power of, this is nothing but modulus of T star. So in this case, null space of T equal to null space of T star. So whenever T is 1 to 1, automatically we become unitary. So if T is 1 to 1, then V is unitary in the polar decomposition. So in this case, when T is normal, you can easily check that V commutes with mod T. If T is normal. Not only that, we can also check that V is also normal. This can be proved using the definition of partial isometry and normality of T. Okay. If T is self-adjoint, then we can say that V is also self-adjoint. equal to V star. These are some observations about the polar decomposition. Now let us look at some examples which illustrate the polar decomposition theorem. Let us start with simple example. Take t equal to lambda I, where I is a map from H to H, the identity operator. Lambda is a complex number. Now we can write lambda as mod lambda e power I theta for some theta. So mod t, so here tx is lambda x, mod tx is mod lambda x, and we can easily show that Vx is e power I theta x. Let us try to look at this, try to generalize. Look at an operator t from C2 into C2, which is given by the matrix lambda 1, 0, lambda 2, where lambda 1, lambda 2 are complex numbers. You know that this is a normal matrix, and t is positive, different only. Okay, so we want to look at the polar decomposition. So mod t, we have already observed in the earlier lecture that this is nothing but mod lambda 1, 0, 0, mod lambda 2. So we can easily guess what is V. In this case, V is e power I theta 1, 0, 0, power I theta 2, where lambda 1 is mod lambda 1 e power I theta 1, and lambda 2 is mod lambda 2 e power I theta 2, where theta 1, theta 2 are real numbers. So this is the polar decomposition, t equal to V mod t. We can slightly generalize this result again. So let us take a complex sequence, lambda n is a bounded sequence. Define t from L2 into L2 by txn as lambda n xn for all xn in L. That means we have t of x1, x2, x3, so on is lambda 1 x1, lambda 2 x2, lambda 3 x3, so on. Now the matrix of t with respect to the standard orthogonal basis of L2 is given by, I am not writing the basis here, but this is understood. This is lambda 1, lambda 2, lambda 3, so on. So mod t, as we have observed earlier, this is nothing but mod lambda 1, mod lambda 2, so on, mod lambda n. And we can actually look at e power I theta 1, e power I theta 2, where lambda n is mod lambda n e power I theta n for some okay. So in this case we can easily show that t equal to V mod t. So based on this I can give few exercises. So whenever you write a polar decomposition, you have to check that null space of mod t equal to null space of P. So let let T be a positive operator. Write the polar decomposition. Let me mention again. It may be possible to write T equal to V1 mod T, that equal to V2 mod T. But whenever null space of the partial isometry equal to null space of mod T, then only we can say that it's a polar decomposition. Otherwise, it's not a polar decomposition. So you should be very careful while writing the polar decomposition of an operator. Let us take where x sigma mu is a sigma finite measure space. Look at them and let us take phi m phi from L2 of x sigma mu into L2 of x sigma mu be defined by then write down the polar decomposition of okay. So this is about the polar decomposition, and let me give one more important result, which is corollary of the polar decomposition result. Let T be a bounded operator from H1 into H2. Show that then there exists a partial isometry W such that T equal to mod T star W, which satisfies range of W is exactly range of T closure. So the idea is simple. You write the polar decomposition for T star. Let T star is V mod T star be the polar decomposition of T. Of T star. So that means we have null space of V equal to null space of T star. This is nothing but range of T part. So we have also T equal to mod T star V star. So this is mod T star W, where W is nothing but V star. Now if you look at range of W, that is nothing but range of V star is nothing but null space of V per, but null space of V per is nothing but range of T closure. So this is the unique decomposition we can write for the operator T. So now what is the advantage of writing the polar decomposition? So let me do following exercises. Let us take a bounded operator T. then we can show that range of T is closed if and only if range of mod T is closed. We can also show that T is bounded below if and only if mod T has a bounded inverse. That means some of the properties of T can be obtained using the modulus of the operator. We know that the modulus of the operator is positive, and we know how to handle with positive operators because they are better than general operators. So from that point of view, we can say that the polar decomposition is more useful in getting information about the original operator T using the modulus of the operator. Okay, so this is some information about the polar decomposition. I'll stop here. Thank you very much.